The next part of 4.6 is Simpsons Rule, which we won't go through the whole proof, but the idea of that one in comparison to trapezoid rule is trying to fit a third degree polynomial to your equation. The fact that it can curve means it can be even more accurate. And so the way that Simpsons Rule works, and they have some of the proof in the section if you're interested and want to see it. Is the formula looks really similar to trapezoid. The only difference is here with the function, it has a slightly different pattern. So similar to trapezoid, the first and last values, function values, are only used once, but instead of all the middle ones being twice, it goes out a pattern of 4, 2, 4, 2, 4, 2, 4. And so sometimes it helps to just completely separately tell yourself the pattern is the first coefficient's 1, and then it goes 2, 4, 2, 4, 2, 4, as many times as you have. And then another thing about Simpsons Rule, the definition, is that your number of subintervals has to be even. And so that way, notice like here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It'll always end with a 4, 1. That way you'll never run into like a 2 and then go, well, what do I do? I'm at the last one. If n is even, it'll always end with 4, 1. Okay, so let's try it on the same example we did trapezoid rule and see if it's more accurate. So from 0 to pi sine of x dx, so b is pi and a is 0, so we have pi over, and let's try to do the same number of subintervals. We'll do 4 again because it's even and it's the number we did on the trapezoid rule, so we can compare which one seems like it did a better job. And so 3 times 4, I'll end up with 12 under there. Okay, so then all my points, I'll have sine of 0, because I'm breaking up 0 to pi into 4 units. So I'll go 0 pi over 4. Each step will be pi over 4. And then the next one is, just notice I wrote down the pattern wrong. So 1, 4. It always starts and ends with a 1, 4. So then I have 4 sine of pi over 4 plus 2 sine of pi over 2 plus 4 sine of 3 pi over 4. And now I'm on my last one, so that one only goes in there once, so sine of pi. And notice by having an even number of subintervals how that ended on 4, 1 again for my coefficients. Okay, so then I'll evaluate all these. So pi over 12 times sine of 0 is 0. 4 times square root of 2 over 2. 4 over 2 will leave you with 2 square root of 2. And then 2 times 1. And then same thing for this one, 2 square root of 2. And then 0. And so I'd add these up, multiply by pi over 12. And what is that? Approximately 2.005. So notice doing a pretty small number of subintervals, we got that to be within 0.005 of what we know the actual answer is, since we know it's 2. So both of these, as far as approximation methods, they're both pretty ingenious, but the real power is to be able to do functions that you can't do explicitly using the antiderivative, so you can still come up with really good approximations